So I'm from the quantum computing effort at Google, and at Google our team has a roadmap to eventually build a fault-tolerant quantum computer. So this is a pretty ambitious endeavor where when I say fault-tolerant quantum computer, I'm imagining something that probably has on the order of 1 million physical qubits, and we're aiming for logical error rates such that we could run computations with billions or maybe even trillions of logical gates. So needless to say, I think this is a challenging and ultimately very expensive endeavor. And when you're in an industry context and you're doing something very expensive, you often get the question of why. Why are you going to do this? And of course, the answer we usually give is because we hope that these devices are ultimately going to solve important and otherwise intractable problems. As scientists, of course, we just find them fascinating. But in an industry context, you hope that they might actually be valuable as well. However, the reality is that while we know of some use cases for a device like what I'm discussing here, something with 1 million physical qubits, there's sort of fewer compelling applications than we would hope. And so I think it's important to continue to sort of flesh out more specifically what we could actually do with such a device. And so this talk is about research into sort of the resources required for promising applications, especially in chemistry. And I want to say I think generally we need more researchers to be sort of practically thinking about how we could use machines like this. So a very brief outline here. There's going to be 3 kind of different sections of the talk that will have each, I think, a very different feel. Because I'm going to talk a lot about quantum chemistry applications, the first portion of my talk, I'm going to give sort of an overview of what I call kind of modern fault-tolerant quantum algorithms for chemistry. And it's sort of going to be a review where my goal is to kind of give some intuition for how I think about how these different algorithms compare and sort of relate to one another. And it's going to be maybe a little bit more on the technical side. In the second section of the talk, which will be sort of the main section of the talk, I'm going to discuss results that our team has had on identifying and assessing the viability of executing various valuable chemical applications on a fault-tolerant quantum computer. And then I'm going to, if I have time, include sort of a quick survey of some recent work on applications in chemistry that don't have to do with electronic structure. Okay, so the first part will be this sort of review of quantum algorithms for chemistry. So I think most people are sort of familiar with the second quantized encoding of electrons, where we sort of have 1 qubit that is for every orbital an electron might occupy. It's 1 if an electron's there, it's 0 if it isn't in most, or at least in the simplest encodings. Basically in this representation, the symmetries are encoded in the operators. The states that we're simulating are not themselves explicitly antisymmetric, so the operators have to act on them as if they are. So there's this, these fermionic anti-commutation relations to the operators, and this gives us things like the Jordan-Wigner transformation, so we can write down a qubit Hamiltonian. And I might note that in second quantization, we tend to get a decomposition into local operators, which I think makes it a bit more nisky than the alternative. And it's also a good representation where you're sort of near half filling or you have a very compact basis, which is often the case if you're working in an active space and you're using molecular orbitals. But another option that's going to be important, and I'll talk about a good bit in this talk, is the first quantized representation. So here, by the way, throughout the talk, I'm going to use eta to represent the number of electrons and n to represent the number of spin orbitals. And so in first quantization, usually the idea is that you have sort of eta different registers, 1 for each occupied orbital. And then each register is of size log n because it's just going to store in binary like the index of the orbital that's occupied. And usually in first quantization, you require that the wave function itself is explicitly antisymmetric. And so then you don't have to worry about the antisymmetry in the operators. You don't have to do things like a Jordan-Wigner transform. So the antisymmetry is sort of explicit in the state. The operators you get, they're sparse, so they can be simulated, but they're not local. And I think that makes it a little bit less nisky, but it's not really a problem within the cost models appropriate for fault tolerance. Now, there's sort of a very different space requirement of these algorithms. In first quantization, the number of qubits you need is eta times log n. So if the number of orbitals is something very, very large, then in terms of the number of orbitals, it's actually exponentially less space in first quantization versus in second quantization. So if you want a really accurate representation, you want to use a billion plane waves or something, and there are use cases where you would want to do that. First quantization, I think, is definitely the way to go. And I'll argue later that I think that makes it particularly suitable for doing dynamics, for example, where you have dynamics of both nuclei and electrons, because if the nuclei are moving, molecular orbitals sort of make less sense. The whole point is they're centered on the nuclei. And if you have to resolve momentum transfer between the nuclei and the electrons, you might need a lot of basis functions. So that also makes it well suited.
Why can't you compress a second quantized picture? I mean, you have, eta choose n or something like that.
Yeah, so
States you actually use.
So for example, it is possible to do things like you could just simulate in the block of fixed particle number in second quantization, but at that point, it's starting to look already a lot like a first quantized representation. So people there have been a couple papers that have done that, and those algorithms generally just are explicitly less efficient than a similar algorithm that would be in first quantization. But it's sort of a fair point. You could try things like that, but most of the time when people talk about second quantization, they're doing something that isn't specializing to that particle manifold.
My question is basic, what is the exact difference between first quantization and second quantization? Whether it is just the representation perspective or because all I can see is both look same to me.
In practical terms, I think that in most cases, but not always, people tend to do this thing where there's a big difference in how the wave function's encoded. So, it would be n qubits in second quantization versus eta log n in first quantization. But I think the more fundamental way people tend to describe the difference is it has to do with where the symmetry lives. In second quantization, the symmetry lives in the operators because the wave function itself, if I just look at the qubit wave function, it's not going to be anti-symmetric, even if it's encoding a fermionic wave function. So the operators have to respect that symmetry. Whereas in first quantization, we're typically requiring that the state is explicitly having the symmetry of the systems that we're simulating.
The operators also have to respect some kind of anti-symmetry.
Not true. So in first quantization, if your wave function is explicitly anti-symmetric, because say the chemistry Hamiltonian is going to commute with the particle permutation operator, then if you start in an anti-symmetric state, the whole evolution is going to remain in that anti-symmetric subspace, and it's not.
It needs to have the same type of symmetry for sure.
It needs to basically commute with Okay, so I'm now going to talk a little bit about methods for quantum simulation as they pertain to chemistry. I think most people are familiar with Trotter methods or product formulas. So often, but not always, Trotter formulas, they tend to sort of scale linearly in the Hamiltonian sparsity. If you have the Hamiltonians A plus B plus C, you're just going to sort of simulate those things in sequence. So you're going to have to touch each of them. But I'd say a lot of the best algorithms for chemistry are based on linear combination of unitary type methods, which I think, as most people know, you start by writing the Hamiltonian as a linear combination of unitaries, which you can usually do. And particularly popular in chemistry is to use these qubitization methods, for example, where the goal is to realize something like a quantum walk that has eigenvalues which are sort of functions of the eigenvalues of the Hamiltonian. So, for example, with one way that you can implement qubitization is with these so-called select and prepare oracles, where basically you can just sort of prove to yourself that if you wanted to implement an operator that had eigenvalues like I'm writing here, you could do that by decomposing it as the following circuit in terms of these things that are called select and prepare. And what's going on here is that you have this unitary called prepare, which prepares a superposition on this thing that we'll call an index register. It sort of indexes, just in binary, every term in the linear combination of unitaries, and it puts that in a superposition that's weighted by the coefficients of the terms in the linear combination of unitaries. So if you have L terms in the linear combination of unitaries, this prepare thing is just on log L qubits. And then you have this other unitary called select, which what it does is it basically is a controlled application of one of the terms in the linear combination of unitaries in a way that's controlled on this index register. And so because if you were to apply prepare, you put this thing in the superposition, and then you apply select, it's sort of like you're applying all the terms in the Hamiltonian at once, and with a weight that is sort of depending on the coefficient in the linear combination of unitaries. And there's also this parameter lambda, which comes up in the definition of prepare, which turns out to be very important for the complexity of these algorithms. Lambda is sort of like the one norm. It's just sort of the sum of the absolute value of the coefficients in the linear combination of unitaries. And it's quite important for the complexity of anything you might want to do with these cubitized operators. So for example, one thing that you might want to do is you might want to prepare eigenstates of the chemical Hamiltonian by performing phase estimation on this quantum walk operator, which would, when you do that, you'll just measure one of its eigenvalues and you'll project to an eigenstate of the quantum walk operator, which is also eigenstates of the Hamiltonian. You can also measure out that eigenvalue and then get the corresponding eigenvalue of the Hamiltonian just by taking the cosine of it, since it gives you the arc cosine of the eigenvalue. And the cost to do that, the cost to apply phase estimation to this cubitized quantum walk is CW is the cost of implementing the cubitized quantum walk times lambda over epsilon. So lambda ends up being quite important for the cost.
I'm sorry, naively it seems that this W, this construction, has cost that which has depth linear in L. Isn't that the case? Because if the
we'll talk about that in the next slide. So this is sort of a key thing here is like, this isn't a complete algorithm. I'm just telling you in terms of these oracles, select and prepare. The big question is, how do you implement select and prepare in an efficient way, right? Also, if you wanted to do time evolution instead of phase estimation, you can use quantum signal processing with this cubitized quantum walk, and you get a cost that, again, is going to be linear in this lambda parameter times the cost of the quantum walk. Okay, but as you've asked, how does the quantum walk scale? I'm not going to go into great detail about these things, but I will say that generally select is the easy part for chemistry, because what select has to do is it has to determine like which of the terms in the linear combination of unitaries is it going to apply, and then apply it. And if you just index the terms in a reasonable way, like that you can do things, you can do logic, like you can apply the Jordan-Wigner transformation of the term, for example, just using logic, and then just apply the corresponding operator. So this tends to be quite easy, and it's quite straightforward to, in first quantization, implement select with a number of gates that up to log factors is just scaling like O of eta in first quantization or O of n in second quantization. Somewhat surprisingly, the hard part where the cost tends to come into these chemistry algorithms is the prepare step, which it's a little surprising just because you're acting on a log size register, but you're preparing a very complex state on that log size register. And the sort of heuristic I'm going to give you for understanding, I'm not going to go into detail about exactly how this works, but the heuristic I'm going to give you for understanding the cost of the prepare procedure is that it tends to go, in most cases, what people tend to do for prepare, unless you have some very special like analytical structure in the coefficients, you have to do some technique for state preparation, which involves sort of looking up the coefficients of every term, essentially from a database using coherent logic. And if you're actually going to instantiate that as a circuit and not just like wave your hands and claim QRAM, which is something I don't believe in, and most of the literature that actually does resource estimates also doesn't believe in, then it turns out that the cost, which I'll sort of define to be something like the number of Toffoli gates, tends to go like O of square root gamma. If gamma is basically like the size of the database required to store all the coefficients. So it's kind of like the amount of information required to specify the Hamiltonian. So I'll give a couple examples of this so you'll maybe understand a little bit what I'm saying. In second quantization for chemistry, this is usually what the two-body operator, the Coulomb operator, looks like, which is usually the hard part to implement, and it's hard because this is the part with like n to the 4 coefficients, whereas the one-body part just has n squared, so this is sort of the part that we'll focus on. And so this gamma is like n to the 4, because there's sort of n to the 4 pieces of information, and then using the formula I showed you on the last slide, the phase estimation cost would be about n to the 4 over epsilon, where we're recalling that the total phase estimation cost is like lambda times the cost of the quantum walk, divided by epsilon, and the cost of the quantum walk is like square root gamma. So in this case, square root of n to the 4 is n squared. And basically for all these chemistry systems, lambda is like n squared. So that's how we get n to the 4. So that's one algorithm that you can implement. But some of the like sort of more contemporary algorithms, what they do is they use tensor factorizations of the electronic structure Hamiltonian in order to sort of reduce the amount of information that you have to store and look up in this database. So you can do something called a Cholesky factorization of this operator, which is basically just rewriting this two-body operator as a sum of squared one-body operators. And it turns out because the Coulomb kernel is low rank, in general, you would probably expect that you need to have like a sum of n squared different squared one-body operators. But for the Coulomb kernel, you only need to have a sum of n different squared one-body operators. And that means there's only n to the 3 pieces of information. And so that means that the cost of the quantum walk is like the square root of n to the 3, which is n to the 1.5, times n squared gives you a phase estimation cost. It's like n to the 3.5. Even sort of more recently, there's this way that you can express the coefficients in the Coulomb operator that has been known in chemistry and studied in that context for a while, which these chemists call it tensor hypercontraction, but it's a particular tensor factorization that you write like this. And basically, in this case, there's 4 tensors, but each of these tensors is O of n by O of n. So there's only n squared pieces of information required to specify the Coulomb operator. And then you are able to get down to a phase estimation cost that's like n cubed over epsilon. And so that's kind of like a summary. These are sort of currently the 3 best algorithms for second quantized molecular orbital chemistry simulation.
Does that work for every V or for special cases?
This works for for basically the Coulomb operator in an arbitrary basis. So it doesn't matter your basis, but the V has to be coming from like integrals over the 1 over r operator, which is always the case. Well, it's special, but that's the only V that is ever physical for electrons. So yeah. Okay, so now you might say, well, hold on a second. I mean, what if I chose a basis in a smart way? Like I chose the basis to be grids or plane waves. And in that case, you actually have analytic integrals. So like I can actually just write down an expression that maybe looks like this for the Coulomb operator. So I don't need a database to look up the operator. Would it still scale like what I just said? And the answer is no. In that case, you can do better. And so that's why there have been a lot of papers that are looking at simulating chemistry in these simpler representations. But the problem is, if you're going to use things like plane waves or grids, you get this really simple and easy to qubitize quantum chemistry Hamiltonian, but you need a lot more grid points or plane waves to simulate a molecular system than if you're using, say, molecular orbitals. In fact, to reach chemical accuracy, it's often a factor of like 100 to 1,000 times more. So a system that might be well described by a couple hundred molecular orbitals might need 20,000 or 200,000 plane waves to describe it to a similar level of accuracy. And in second quantization, that's a major problem, because in second quantization, the space complexity, unless you're doing something quite unusual, tends to just be scaling linearly in the number of basis functions. And 20,000 or 200,000 logical qubits is sort of a non-starter. But in first quantization, this is seeming much more practical because the space complexity is just the log of that number. So for example, if you wanted to simulate 60 electrons in a massive 100,000 plane wave basis, that would be only 1,000 logical qubits, which is something that in my mind sort of fits on the million physical qubit quantum computer that we're aiming to build. And so
So yeah, just one quick question, but in the really extreme case, for the first quantize, and you just have eta equals 1, which is basically nonlinear Schrodinger operator. Mm-hmm. And if you ask applied math people how many bases you need to get enough information for nonlinear Schrodinger operator, actually the number of bases could be really large.
Mm. Okay.
So the cap n actually could be really large, even in the extreme case, it sounds like.
Well, first, I'm not simulating a nonlinear Schrodinger equation here. I'm just going to focus on the sort of linear one with Hermitian operators and such. But if you just have one electron, there's also like a whole lot of other games that you can play because it's non-interacting, it's closely algebra, and there's special ways we can simulate that. But
there's no collider interaction.
What's that?
There's no Coulomb interaction with one electron.
Right, yeah. But also, I mean, I guess first quantization could still be a way to deal with this because, I mean, it's practical to do a first quantized simulation with 1 billion basis functions because, you know, you're only needing the log of the number of basis functions. Now, it turns out that you have to be careful because the gate complexity might still scale polynomially in the number of basis functions. And there were papers going back like to about early 2000s that were looking at first quantized simulations of electrons, but they were having scaling that was kind of bad polynomial scaling in the number of basis functions. But more recently, starting in 2018, there were these papers by the Google team that showed there are ways of doing first quantized simulation that they still scale polynomially in the number of basis functions, but sublinearly. So we got down to scaling like n to the 1/3. So that really isn't that bad. And like I was saying before, I think this is particularly attractive for non-Born-Oppenheimer dynamics. And another interesting thing about using simple basis functions like plane waves is because they don't depend on the nuclei, you can just sort of talk about the cost of these simulations in a way that's independent of the molecule you're simulating. You just need to know what's the target precision, you know, how long you want to simulate for, what's the basis size, how many electrons, and what's the Wigner-Seitz radius, and you can already figure out just from that exactly what the cost will be. So the analysis, I think, is much simpler. So anyways, that's sort of my review of how these algorithms work and how I think about how first and second quantized algorithms and with different tensor factorizations relate to one another. And so we've done a lot of work on that, but I'm now going to talk about sort of the search for applications of these algorithms. And if you've been in the space a while and you've heard people sort of talk about, you know, quantum simulation of chemistry, you've probably heard this whole story about this Foka molecule. It has to do with nitrogen fixation and fertilizer. And there have been a lot of papers that took this one molecule that was proposed a while back as a good application of quantum computers. I won't repeat the whole story about it here. And there have been like actually a lot more papers than this, like 20 papers that have done resource estimates specifically for this Foka molecule. And they've done that because the people working on that were in a lot of cases algorithms people and not chemistry people. And they just wanted to sort of see, you know, how their algorithm compared to what came before it. And this is what other people looked at. So it just became this sort of canonical benchmark. And I think it's illustrative to sort of look at sort of how these costs have decreased over time since, you know, this first paper from Microsoft started getting, you know, concrete T-gate costs. They're saying it's about 10 to the 14, but, you know, there were some estimates going back even before that involved algorithms scaling like n to the 11 that didn't count exactly the number of gates, but it was clearly like in the, you know, more than 10 to the 20. So the costs have come down a lot over time. And I should say that, you know, some of this has come from just like these better factorizations, as I was saying before. But anyways, I think it's kind of boring for us to always be talking about Foka, and it's important to ask, you know, what are some other problems that in chemistry that quantum computers can solve? And in particular, you know, I think it's important that we try to aim for applications that could be doable with a reasonable number of resources, and we can argue about what reasonable is, but in my mind, you know, ideally something that we could do with a few thousand logical qubits and maybe less than 1 trillion Toffoli gates, you know, I think is maybe a good vague target for the first generation of fault-tolerant devices. And, you know, I think it's important to try to be specific about, you know, what we're going to say the quantum computer can do. Like we want to measure this correlation function to this precision so that we can resolve this physical phenomenon. And then we can also look at a classical competition and argue that might or might not work. So the team, I'm going to just kind of skip through a couple examples now, tell you at a high level about them, and then I'll go into one example in more detail. But the team at Google has had a few different projects that have been trying to sort of analyze the viability of particular applications. We spent a while working with the pharma company Boehringer Ingelheim on working on finding good applications in the pharmaceutical industry, like for drug discovery, which was difficult because most drugs are organic molecules, which are not strongly correlated and don't need a quantum computer. You can solve them with a classical computer. But it turned out that one problem that does come up quite a lot is when you make your drug, there's this enzyme that's in your body, which is called cytochrome P450, and it's an iron porphyrin complex, iron and sulfurs, that actually looks kind of similar to Foka, which is also iron and sulfur, and it is a very strongly correlated molecule. And it turns out that this enzyme actually metabolizes 70% of target drug molecules. So basically, if the drug you're making binds to this cytochrome P450, we'll just pee it out before the drug is able to take any effect. So it's important to predict, is this going to happen or not? And it's very difficult because this is a very strongly correlated molecule. And like I said, there's not a whole lot of examples of these things in pharma, but there are some at least. And so that was sort of a use case that we ended up studying in a good bit of detail. And we actually ended up running some very large DMRG calculations that were actually some of the largest DMRG calculations ever run on an enzyme in the course of this to sort of figure out, where DMRG is sort of running out of steam to treat this thing classically. And it runs out, or at least you cross over into the point of quantum advantage at around essentially 80 qubits, 80 spin orbitals, but you need about hundreds in order to have enough precision to resolve the chemistry of the system to work out the mechanism and predict its binding. And so in that regime, it's looking like these calculations would be about what we're aiming for. It require about 3,000 logical qubits and about 10 to the 10 Toffelees. So I'll say that, for molecular use cases, it can be kind of hard to find cases that are sufficiently strongly correlated, but when you find them, I think the resource estimates do often tend to come out somewhat reasonably. Another project that we looked at, though, was in ab initio simulations of solid-state systems. And here we worked with BASF, which is the world's largest chemical company and makes a lot of batteries and has divisions that do computational studies of batteries on sort of assessing the prospects for quantum computers to help with better developing battery cathodes. Most battery cathodes today that are, say the ones in your laptop or your car, they involve Cobalt, which is difficult to mine in ethical fashions. It's very limited, it's expensive. So people have wanted to get Cobalt out of these batteries for a long time. And a good candidate, people thought a good candidate replacement would be these lithium nickel oxide, so-called LNO batteries, cathodes, but that hasn't really panned out. And in particular, the chemistry of those systems isn't well predicted by tractable levels of theory, at least not the ab initio level. So, for example, there's sort of this effect called Jahn-Teller distortions, which I won't go into, but it's something that DFT predicts to be Jahn-Teller distorted, but in practice it isn't. And it's not clear why that is. Presumably you need more correlation than DFT can offer to resolve that. And it's, what's very challenging about systems like this is in the solid state, I think it's fairly easy to find ab initio systems that are sufficiently strongly correlated that you can't treat them classically. But part of the reason for this is because you tend to need to treat a lot of electrons because you have to simulate more than one primitive cell to sort of resolve if you're going to do correlated calculations. And just the size of the system tends to grow relatively rapidly. And this is also going to present a problem for the quantum computer, though, because you just have a bigger system to simulate. So one thing that we focused on in the course of this project was sort of adapting these tensor factorization procedures so that they could take advantage of abelian symmetries in the system. And this is especially important for translationally invariant systems in the solid state. And in fact, you could sort of linearly reduce how the cost of the quantum algorithm scales with the number of k points by doing this, which is helpful, but ultimately not helpful enough to make this what I would consider to be particularly tractable, because it turns out that for this system, we have indications that in order to sufficiently resolve the chemistry that we need to resolve, we need to go to a few thousand electrons, basically. And that would be giving us a number of Toffoli gates that's on the order of 10 to the 15 or 10 to the 16, which is too many. And so I think that there's still sort of a lot of work to do on quantum algorithms for ab initio solid state calculations that need to be developed. I think that there are some methods around how we could better coarse grain these systems, or how we could use methods like DMFT or DMET, purity solver type methods. And there has been some work on that, but I think that there needs to be a lot more to get that to really be practical for quantum computing. There's a lot of trade-offs, like if you do these impurity solver things, there's now these outer loops, which are like iterations, which are multiplying your cost, but you have a smaller system size, and there's considerations about how these things converge in the presence of the type of noise you'd expect from, quantum calculation, and there's other complications with that too. So that's where that is. So one question I want to ask now is, in all of these cases, we've really been focusing on systems that, like are a metal or, have this like very strongly correlated center. And, the question is like, are only the most highly entangled systems promising applications of quantum simulation? Now, of course, most chemical compounds are not that strongly correlated. In fact, can be treated quite well with things like mean field methods or density functional theory. And so, if there was some way that you could use a quantum computer to actually speed up those methods, I would argue we should aim for more than a quadratic speed up over those methods. That could potentially be quite important. And I want to argue for a second, in case people aren't familiar with this, why I think it's important to do better than a quadratic speed up. It's because there's essentially a very large constant factor slowdown associated with implementing quantum error correction. So if you think about the space-time volume required to implement a classical NAND gate in CMOS, it's something like 10 to the minus 9 transistor seconds. But the equivalent of a NAND gate, which is like a Toffoli gate, executed on a quantum computer requires state distillation, and with sort of the error rates that we're targeting anyways, the space-time volume would be on the order of 10 qubit seconds. Now, a qubit and a transistor are not exactly the same thing, but in some sense, there's like a 10 order of magnitude constant factor slowdown here. And that means that if you want to get to quantum advantage, you really need to lean on the scaling advantage. And if you have only a quadratic advantage, it takes you a very long time to overcome like this huge constant factor slowdown. And in fact, there have been several papers. One is this perspective piece that we wrote, but for example, Matthias Treuer and others at Microsoft wrote one quite recently that came to a similar conclusion, which is if you have only a quadratic speed up, then you often, in fact, typically need to go to exorbitantly large problem sizes that wouldn't be practical for either a quantum or a classical computer in order to reach the point where you cross over into a quantum advantage. Whereas if, and it's a little hard to do the analysis like completely in the abstract, but you can try. And it turns out that when you have something looking more like a quartic speed up, the story's changed. Already there, it starts to look much more promising that you'd be able to get to a practical quantum advantage. And I should say that these conclusions don't really change, even if you were to reduce this constant factor discrepancy by a few orders of magnitude. So even if there was somehow like a huge savings in how we'd realize error correction, it's probably not going to massively change this story. Okay, so I'm now going to tell you, we had this paper out earlier this year that came out this summer, and this is work I did with Junho Lee at Harvard, that was actually arguing, in fact, in some cases you can get more than a quadratic speed up over classical mean field methods when the goal is to simulate electron dynamics, but not to prepare ground states. And so again, I'm going to use this notation where n is the number of basis functions and eta is the number of electrons. And I should say that on the face of it, this is like very surprising that we could get a speed up over classical mean field methods because, maybe often the hand-wavy explanation we give of, why quantum computers are better at quantum simulation has to do something with this argument about, oh, well, the quantum computer can more efficiently represent this entangled wave function. So, like an arbitrary wave function might require n choose eta bits or something, whereas, the quantum computer can order n or eta log n or something. But when we're talking about a mean field, like a system that is actually sufficiently well treated by a mean field level of theory, the whole point is that you don't have to, it's not entangled. You can sort of represent it as, a product or an anti-symmetric product or something of, like eta different wave functions. And so you only need, like the classical storage is only n times eta instead of n choose eta. And it turns out that there's a lot of work in, say, the chemistry world and just generally and other people that work on electron dynamics, for example, in TD-DFT, of figuring out what is the cost of sort of like updating, like doing it one time step of electron dynamics in the mean field level of theory. And that's usually scaling, the best methods for that tend to scale like eta times n. which isn't that surprising. It's got, if it touches all the bits. But rarely in that literature do people sort of do the kind of computer science analysis to figure out like, well, how does the number of time steps have to scale with the size of the system? So anyways, we did that analysis. It was kind of formulaic, but we're able to show basically that the best classical mean field methods are today scaling like what I've written here. And in fact, we're able to find examples that sort of saturate that scaling for how the time step grows with the number of basis functions and particles. So in that sense, the scaling is kind of tight. And it gets worse if you want to simulate systems at high temperature, because there it's sort of like you have more occupied orbitals that you have to deal with. So if you just think about it in terms of the space complexity, it's kind of like you'll need something closer to n squared space complexity because you have potentially all the orbitals occupied. At least that would be the case in like a sort of density matrix type formulation. But it turns out that these, in first quantization, I was already sort of talking about the cost of the first quantized methods earlier. It is possible to have scaling that's much better. Again, I told you that using these qubitization-based algorithms, you can have scaling that's sublinear in n. And so it's, and you only have eta log n qubits. So what's really kind of surprising here is that normally you think about getting speedups in quantum simulation by better resolving entanglement, but that's not what's going on here. Basically what's going on is the fact that even like for a single particle, we're able to, like encode the particle in just log n qubits and sort of do a simulation of it in that representation in a way that doesn't really have any analog classically. And I should say that, for very large n, that's kind of what the scaling ends up looking like. So these are kind of like difficult, messy things to compare to one another. So I have this plot here, which may or may not be elucidating. So what I'm plotting on the y-axis is the speed up ratio of basically what is the, I'm going to write the cost. I'm going to sort of relate n and eta, which is sort of necessary to give a speed up in terms of the overall problem size. So I'll say that n is equal to some theta of eta to the alpha. And then I'm going to sort of say, okay, what's the ratio of the exponent of the scaling for the classical algorithm to the exponent of the scaling for the quantum algorithm? And so if that ratio is greater than 2, it means we have better than a quadratic speedup. And sort of in different regimes, there are different like optimal quantum and classical algorithms to use. But this is sort of what things end up looking like. And the point is that currently at rather small, basically when n is sort of comparable to eta, we have a modest super quadratic speedup. And then when n is much, much bigger than eta, we have a speedup that is bigger than quadratic and further grows as the relationship between n and eta grows. So yeah, and the other thing to emphasize about this is that this is comparing to a mean field level of theory, but this is using an exact quantum algorithm for simulation. So this is comparing apples to oranges here in a way that is, highly beneficial to the classical algorithm. If we have a system that is not well treated by mean field level of theory, maybe it doesn't need like exact quantum dynamics, but it needs something more like DMRG or like a couple cluster sort of level of theory to do the update, then you would expect a much bigger speed up of the quantum algorithm. And so I think that that is encouraging. But also, it turns out that the prospects for speed up look much better at finite temperature for the reason that I was describing before, that the classical algorithms, when you're doing mean field, are scaling worse at finite temperature, which is a little sort of counterintuitive because you often think finite temperature is maybe like a little bit less quantum or something. But again, the speed up here isn't sort of coming from better resolution of the entanglement. So the considerations are different. So I think that this kind of argues a great regime to look at would be what's called the warm dense matter regime. So basically there's something called the hot dense matter regime, which is where things are so hot that they are actually very well treated by a mean field level of theory. But in the warm dense regime, you really have to account for temperature. However, you have basically the Fermi energy is sort of similar to the temperature, and so you really need to sort of resolve correlations in the system as well. And this partially motivated this project that I think Andrew Bukowski here spoke about a couple months ago at the like scientific applications of quantum computing IPAM session. And I have just a couple slides about it here as well. But it was this project that we did that was about trying to use quantum computers to model materials in extreme conditions that are very relevant for modeling fusion reactors. And in particular, Andrew's team does some of the theoretical modeling for this experiment at the National Ignition Facility, which does this inertial confinement fusion thing where these lasers hit this you have this fuel, like deuterium fuel, that's covered in some type of ablator material, which then vaporizes when the laser hits it, and it compresses the material. And fusion may or may not happen, but sometimes it does happen. And recently the National Ignition Facility has had some results where the energy going in from the laser was less than the energy they got out from fusion, which is very exciting. Still far away from a power plant, but exciting nonetheless. Anyways, it turns out that one of the big sort of bottlenecks to doing classical models to predict sort of the conditions of inertial confinement fusion is computing this property which is called the stopping power. So what stopping power is it's basically the drag on, it's like the force of friction on an alpha particle, for example, as it flies through one of these heated plasmas. So basically, as fusion occurs, you get things like alpha particles shooting out, and then it will fly through this plasma, and it will interact with the plasma, which slows it down, which does work on the plasma, which increases the temperature, which causes more fusion in the plasma, and you can see how this is an important heating process. And it's an important heating process in the warm dense matter regime before you actually have the conditions for fusion. That would actually, ignition occurs in the hot dense matter regime, but this occurs in the warm dense matter regime. And anyways, so Andrew's team at Sandia, the DOE in general spends billions of CPU hours computing stopping power with TDDFT. And TDDFT, it's actually not a very good choice for this because it's the warm dense matter regime. So we know that it's not really accurately resolving the correlation in the system, and nonetheless, they do it because it's really sort of the only thing that they can attempt to do. And I sort of, let's see if this video is helpful. Yeah, so this is kind of a picture of like the wave function of this alpha particle as it flies through this plasma. And that's basically what we want to simulate. And we want to measure something like the kinetic energy of that projectile as a function of time. And you can get a plot that looks like this. This is actually the work, so equivalently, the work done on the system. And you can see as this thing flies further into this plasma, more work is done and the energy of the plasma is increasing. And basically, the stopping power is like the slope of this thing. And in particular, you really want to know the slope of this thing as a function of like the velocity of the projectile, for example. Oops. Whoa. Okay, yeah, that was my next slide. Okay, good. Anyways, we ended up doing resource estimates for this system using first quantization. And I should emphasize, I think this is actually like the first example that I know of doing resource estimates for like an ab initio dynamics simulation that is sort of claimed to be of relevance for like an actual application pertaining to some sort of technology or something like that. So we ended up also comparing it to phase estimation just to kind of get a sense of how requirements were comparing. And maybe not surprisingly, we found that in some sense it's a bit cheaper than phase estimation. In any event, here I sort of give the number of Toffleys you need using a couple different methods of implementing the time evolution using quantum signal processing and Trotter and first quantization, which if you use sufficiently high order formulas, it's possible to also get sublinear scaling in the number of basis functions. And I also am saying how many logical qubits are required total for these different simulations. It's sort of the first time that I think an application like this has been looked at, and I think there are still ways to think about improving how we did the simulation. But the numbers as a first stab are not, to me, crazy. 10 to the 13 Toffleys is an okay starting place. And so, anyways, I think that's sort of an interesting story. I guess maybe in just a couple minutes I have left here, I was going to just randomly survey a couple different results which we've had recently, which are not about electronic structure, but I think do have some relevance or interests to well, to chemists in particular. I guess this is not really a chemistry thing, but regardless. So one of them is this result that either Robin Cathari or Rolando Soma spoke about in the first of the IPAM workshops, which is this result we had, which Robin presented this week at Fox, which was about an exponential speedup in simulating these systems of coupled classical oscillators. And I don't have time to sort of get into the details of the results, but maybe a high-level description is this. It's possible to write Hooke's law as something like this. This is like Newton's equation for coupled springs. I've just sort of put the mass term and the like spring constant term on the same side of the equation. So there's sort of this is just like a position of the springs, and it's a vector because there's different oscillators. And a very simple way to kind of understand what's going on here is if you just sort of add this term to both sides of this differential equation, because you can do that, then you can sort of look at this thing and sort of squint at it in the right way. And if you just sort of regard this thing inside the parentheses as like a wave function, and it appears again on this side, you can see the form of this equation is very suggestive of a Schrodinger equation. It's the form like d dt of psi is like I, in this case, square root a of psi. So it would be like a Schrodinger equation under something like the square root of this A matrix. And as a result of that observation, if you're kind of careful about things, it turns out it's possible that you can use quantum simulation to affect evolution under an exponential number of coupled classical oscillators in time that's, or maybe if I just have n coupled classical oscillators, this quantum algorithm can in principle run in time that's only polylogarithmic in n. But that's only the case if there's some sorts of circuits that can efficiently tell you what the mass of every spring and what the spring constant, the mass of every mass and the spring constant of every spring is. And I think there are a number of situations where that's very practical. We also show very strong evidence that the problem has an exponential quantum advantage that you're not going to dequantize because we show the problem is BQP complete. We also prove a relativized exponential speedup in an oracle saying, so no complexity theory required there.
It's very good intuition why it's practically relevant. I mean, I think it's a nice result, but why it's practically relevant, because I understand you get an exponential compression in space, but not in time, right?
No,
So
it's also it's also an exponential advantage in time.
Where
Yeah.
you get the time advantage.
So the polylog here I'm saying that we can simulate this thing in gate complexity that's polylog n, whereas classically it would be polynomial in n.
I understand that, but,
yeah.
but I mean, if I want to simulate the dynamics of that equation for a certain time, you will have to evolve for the same time, basically.
Sorry, the scaling in the time is the same. That's right. Yeah.
Right. So you would need a very large system of harmonic oscillators, which you want to simulate for a comparatively small time and constant time, right? So
yeah.
Is there some natural use cases?
So I suppose it depends on like how the system is coupled. So I think that if it's like coupled in a way that's spatially or geometrically local, then you probably would need to go to times that are polynomial in n in order to like have relevant effects spread across the system. But if you either have initial states which are like very non-local initial states, or you have the system being very coupled in a way that isn't geometrically local, then you can have the system have very interesting non-trivial dynamics in time that is independent or logarithmic and n.
I'm just wondering if there's like practical examples.
Yeah.
Concrete practical examples.
Well, we're working on the practical
one of them.
examples. We've got, but you're right. I mean, it's still sort of a challenge, but we do actually have a project on that. But I mean, I brought it up in the context of like chemistry or many-body. I mean, it's not really like quantum many-body stuff at all. But for example, I think that if you want to do simulations of like vibrations in solids at like sort of a nanoscale or like mesoscale or something, I think that you can often model solids as systems of balls and springs, and in fact, in this regime, when the dispersion relation is low, you can start to see this as something like a speed up for simulating the classical wave equation, but you can also even think about trying to simulate systems like vibrations in complicated molecules like proteins or something like this. So I think that's kind of interesting. Maybe another thing maybe this will be like my last slide before I go to the conclusion here. Another area that our team's been working on, which I think is kind of interesting, is actually not really motivated by fault tolerance, but motivated by trying to find anything that could have practical relevance that we could maybe hope to do in NISC. And of course, our devices are spin models on lattices. So if you're in quantum simulation, it makes sense to think about, okay, when is the dynamics of spin models on lattices going to be relevant? And there's a lot of applications in condensed matter physics, but in chemistry, one system that a lot of chemists care about is basically the NMR Hamiltonian, which looks like a sort of Heisenberg model. If you want to sort of predict what an NMR spectrum is going to look like, you have to simulate the time dynamics of these Heisenberg models. And it turns out that in most cases where you usually perform NMR calculations, that is something that's easy to do. But there are NMR experiments that you could run, which people typically don't run currently, because basically that inverse problem of trying to figure out what was the Heisenberg model that gave rise to this series of peaks is difficult to simulate. And like an example of a situation where that arises would be if you have something like a protein that is in a membrane, and there's a lot of situations in biology where proteins might be in membranes and you might care about what's going on with them, but in a membrane, the protein can for example, only tumble in like 2 directions instead of in 3 directions. And this gives you an anisotropic Heisenberg model, which ends up having much more complicated dynamics. And so, for example, that's the type of NMR experiment that we're interested in, basically doing a Hamiltonian learning type procedure that involves using a quantum computer to sort of enable characterizing data like that coming from an NMR. So we had a paper about that. And okay, with that, I'll basically wrap up. I think it's critical to identify chemical problems where quantum advantage would be impactful. More things beyond FIMOCA would be good. And we do have, I think, a good number of examples in the molecular space. But generally, there's just not that many molecules that are so strongly correlated that you need a quantum computer. In the solid state, there are, I think, a lot of examples, but there it becomes difficult to fit the problem on the quantum computer as well. And so we need more development in those algorithms. I also told you about these results that quantum algorithms for electron dynamics are sometimes even faster than classical mean field methods, especially when you're needing to resolve some amount of correlation or temperature. We talked about this computing of stopping power of pre-ignition fusion fuels, which has a nice quantum advantage. And I think these numbers can even be brought down a bit further. Yeah, thanks.